Hello everyone. Today we are going to start chapter 15. Okay, section 1. Okay, talk about the double integrals over rectangles. Okay, so let's get it started. Okay, so this is a math 1D lecture 13. Okay, so this is a section 15.1. We talk about double integrals over rectangles. Of course, here we talk about rectangle is the simplest planar region. Okay, later on we're going to talk about a different region. General region, say the region described by curves. Okay, rectangle described by straight lines parallel to x-axis, y-axis. Okay, we talk about those kind of rectangle. Okay, so first of all, let's review. First of all, let's review. We review single integral. We talk about it. Say here we say if f is continuous. Okay. Well, of course we can talk about discontinuous function, but the discontinuity point must be not too many. Okay. But most of the cases when we deal with it, especially in our textbook, we deal with a continuous function. So let's say continuous on this interval AB, on this interval AB. And then, well, for simplicity, we can assume the function is positive and also assume AB are positive. Say suppose this is A and this is a B. Of course, the function can be negative and A can be negative, B both can be negative. Okay, just for simplicity. Well, we try to find, say, the volume under the curve above x-axis between A and B. So we said this is y equal to fx, and then this is the x, this is the y-axis. So what we want is to find the area. Okay, we say find the area, capital A. Okay, how do we do that? Okay, remember we say 4 steps to define definite integral. We say, well, first step, we do partition. Okay, partition, we do this, we say A is called x0 less than x1 less than x2 less than, okay, we say less than xn. Okay, we say this is called a partition. And then second step, we do approximation. Approximation. Okay, how do we do approximation? Approximation basically is like this. suppose this is a xi minus 1, and this is a xi. Okay, we take a point here. We call this point, say, xi star. Okay, now xi star is between, so here we say, well, let me put it here, xi star is greater than equal to xi minus 1, less than equal to xi. And then we evaluate function value at that point. So this, suppose this is function value. And then we create a rectangle. Okay, we create a rectangle. Then we use this area of this rectangle to approximate the area under the curve. Okay, so that's the approximation. So approximation is fxi star, that's the length of the rectangle. And the width, of course, is the xi minus 1. Now, sometimes we call this xi minus 1, we call it delta xi. Okay? Now, if we have, sometimes we have equal spaced partition. If we have equal space partitions, so that means the distance between x1, x2, and x2, x3, x3, all of them are equal. Then this increment delta xi, then we're going to call it delta x, because that's independent of I. It's always equal to b minus a over n. So that's length of a subinterval, right? Okay, now because we do equal space partition, that's the simplest partition. Theoretically, we can do any kind of partition. Okay, now here, say third step, we do summation. Okay, summation. So we add those approximation up. Okay. Then we say, we add them up, like I say here, I from 1 to n. And then f xi delta x. So assume we use equal space partition. Now you can see on each subinterval we have an approximation. So this basically, this is approximately equal to the area. Okay. Now, if the interval is small, we have a better approximation. So you can check your textbook has a better picture draw there. Okay. Then we say the last step. Okay. Last step, we say is taking limit. Taking limit. We take a limit, we say, well, we put it like this, a limit. We let n goes to infinity. Well, if it's an equal space partition, okay? Now, if it's not an equal space partition, then when we take a limit, we want to guarantee the length of largest subinterval goes to 0. Okay, that's more detail. And then our book, this textbook, only talk about equal space partition, okay? And then we say, well, this is the f xi star delta x. Okay. Now this limit may or may not exist. So here we say if limit exists, we say if exists. Okay. Then we define this summation be the integral from a to b, fx dx. We call that's the integral. And then that's the area. That's the exact area. That's how did we define the definite integral. Okay, so you can review your math 1b. Okay, review math 1b, I believe is in chapter 5. Okay, for the definition. Now, today we're going to talk about double integral. Okay, let's see. So here we say 2. Okay, we consider function of two variables, f, x, y. Okay, function of two variables. Now, function of two variables, we say in the three-dimensional space, that's a surface in the space. So here, let's see. Suppose we have this surface. Okay. Okay. Let me see. Okay. And then we say, let's look at this. Okay. How about it? Let's see. How about we draw a picture? Okay. So we have x, y, z. Okay, how about we say we consider this in the first octant? Okay. Yeah, I think I need to draw a straight line. Okay. Okay, let me see. Okay, so here, this is like a, on the, maybe, okay, let me see. Okay, so it's like this. Maybe I should also put it the x-axis a little bit longer. Okay. Okay, like this. So here is like this. Say we said this is z equal to f x y. Okay, now this is a function of two variables defined over the planar region. Suppose here, this is A, and then here is B. Here, this is a C. Yeah, I think that this, I also need to put it this a little bit longer. Okay, so this is a D. So that means we say, well, suppose this region we call it R. Okay, we say this one defined over R. R is this rectangle x, y. Now we say x is between A and B. Y is between C and D. Okay, we have this. Now, if we want to find a volume, find volume. Okay, find the volume of a solid region under the surface above x-axis over R. Okay. Okay, so here, how about we say, if I call this, say here, this is a V. Okay, volume V. How do we find that? Okay, well, we're going to do same thing. We do the 4 steps. So first of all, first step, we do partition. Okay, partitions. This time we have this A is equal to x0 less than x1 less than x2 less than xn equal to b. And then C equal to y0 less than y1 less than y2 less than, well, here we say y sub m. Okay, n and m may not be the same. Okay, so we do the partition. Now you see here, I don't need to do all of them. How about I just do one of them? Say here, suppose we say here this is xi minus 1. And then here, well, to be easy to see, I make this a little bit larger, xi. And then I'm going to say here is, say this is a yj minus 1. And then here is a yj. Okay, so now we're going to look at it this, say here, we're going to look at it this, this subpatch, okay, or subregion, okay, on R, okay, this one. We're going to look at it this part, okay. Now, on this part, we're going to draw the approximation. Well, you see here, on this part, let me see. Here we say, we draw this one. Yeah, I think it's happened to be, oops. Let me see what I missed. The y-axis. Okay, I think maybe I should just, this is like, we're going to have something like this. Well, okay, something like this is happen to be here. And then, well, we have this one. Happen to be here. Yeah, I think this is a little bit, I think I should, okay, well, something like this. So here we have this patch. So here we have that, something like that. Okay, and then if you think about, we pick a point here. Okay, so this point, we say that's xi star, yj star. Well, where xi star is between xi minus 1 and xi. And then yj star is between yj minus 1 and yj. And then we find the function value corresponding to the point, say supposed here. Okay, and now instead of use a surface, so this time we use a horizontal plane. The height is this f is fxi star, and then yj star. So here is like this. So we consider this rectangle. Okay, so you think about a rectangular box is like this, rectangular box. Okay, so now we say we do the hopefully you can see the blue curves. Okay, so second step, again we do approximation. Approximation, this time we use this to say here f xi star y j star. I noticed your book uses xij star yij star. In fact, the index x should not depend on j, and the index of y, the index of y should not depend on I. So if you read your book carefully, you can see the difference. I think probably that's a misprint. Okay, so here we say, well, this one you multiply delta xi times delta delta yj. What's that? Okay, so you think about this is a okay, I'm going to draw the picture here. How about I'm going to draw a picture over here. And then you basically use this rectangular box. Okay. You use this rectangular box. Okay. Now we say this side is delta y. Well, yj. And this side, this side is delta xi. And this length is f xi star yj star. So width times length times height, that's the volume for this rectangle. You see the top is a flat, right? Okay, because at every point we have the same height. So that's the approximation, because the real case is that on the top is the surface. Okay, at a different you have a different height. So this is the approximation. Now, if we say again, if I use equal spaced partitions. If I use equal space partitions, then we say delta xi is equal to delta x is equal to b minus a over n, just like before, and delta yj is equal to delta y. We say that's equal to d minus c over m. Okay, so that's like this. And then with the third step, we just do summation. Okay, summation. So you see, on each area we have a rectangular the box, and then on the whole region R you have many rectangular box. So you add them. Well, you see you have n rows, m columns. So here when you add them, well, your book uses one summation, and the bottom both m and n. I'm going to use two summations. I start from 1 to n, and j start from 1 to m. Okay, usually we put it this double summation, then f xi star y j star. And then here we have delta x, delta y. Okay, remember this also we call the Riemann sum. Riemann sum, if we say this is always an approximation of the volume, okay? Well, you may get a good approximation or you may get a better approximation. If the partition get finer and finer, you get a better approximation, okay? So you see our computer calculated integration, definite integral. In fact, the computer have a software to do the approximation because you can't, no matter how powerful the computer is, you cannot do infinity. So here we say take a limit. The computer cannot take a limit. They always say give a large enough n value, and then the approximation is good enough. So here we say number 4, take a limit. Okay, let me just write a limit. Okay, now the limit, then we say this is like this m. Your book uses one limit. I'm going to use 2. N goes to infinity, and the m goes to infinity. And then we have this I from 1 to n, and then j from 1 to m. And then we have f xi star y j star. And then we have delta x, delta y. Now this limit may or may not exist. If it does not exist, we're going to say the functions are not differentiable and not integrable. If exist, same as before, we say if the limit exists, then we say we define this limit, and define as, define the limit as this. We use this double integral. Okay, f x y, and then here we use a dA, and that's like say here the base area, okay, the sub area, okay, we put it like this. So this is we say double integral representing the volume, okay, and then we say this is the exact volume. Now for some function, okay, of course the limit may not exist, and the limit goes to infinity, or the limit, you don't have a limit, the oscillator for errors for some very special functions. Then we say you cannot find the volume, or the volume does not exist, okay. Now this is a definition. Well, we said double integral represents the volume of a function of 2 variables, okay. And then fortunately, when we try to calculate the double integral or find a volume, we rarely use a definition, because definition you need to have a Riemann sum. You need to simplify as an expression of an m and an n, and take a limit. Well, it is possible. Like some of your homework problems, simple one, we can do that. But we rarely do that kind of calculation. So here we're going to talk about a theorem. Okay, I'm going to directly talk about a theorem. How do we do the calculations now? Okay, so here number 3, part 3, we call it iterated integrals. Okay. Okay. So let me just state the so-called Frobenius theorem. Well, Fubini is a person, is a mathematician, okay? We use his name to name a theorem, okay? Most likely, he found this theorem. Well, sometimes may not be, because sometimes we use a name to name a theorem, may not be the person found a theorem. That's in math, we have those cases. So we say if f is continuous, over R. So this R we say is equal to a rectangular region x, y, and then x between A and B, and then y is between C and D. Okay? Then we have this. We say this double integral of fxy over R is equal to, we say, here is A to B, and then C to D of fxy. Then here's dy dx. Okay, this is also equal to C to D, A to B, fxy dx dy. Now, here, well, we should understand that this is same as this, A to B, and then we put a parenthesis. Here is a C to D, fxy dy, and then dx. So you can think about it. This is first of all, you integrate with respect to y. The x variable don't change. So after integrate, still a function of x, and then you integrate with respect to x. And then here is, this is the same as, say here, C to D. And then we first of all integrate with respect to x, xy dx. So fxy, that's a function of two variables. So if you integrate with respect to x, you treat y as a constant. So after finish is a function of a y, and then you integrate with respect to y. Okay, so that's like this. Okay, so that's Frobenius theorem. Okay, now let's look at one example. Okay. Yeah, I think we're going to say this section is important to know how to use the theorem to do the calculation. We say calculate this, say 1 to 3, 1 to 5, log y over xy dy dx. Okay, so we just calculated use of Frobenius theorem. So this is okay, I'm gonna call this an integral. Yeah, I think I'll write this 1 to 3 and 1 to 5 log y over xy dy dx. So this is like this. So here we say this is like 1 over 3. Well, remember we integrate with respect to x, y first. So x is like a constant. So I can put 1 over x out. And then here is 1 to 5. Okay. And then, well, this is a log y. D log y. D log y is 1 over y dy, right? And then here's a dx. Okay? Because here x is a constant, so 1 over x is a constant, we can move out of the integration. Okay, so now this is equal to 1 to 3, and then of course, okay, you treat log y as a variable u, so u du. The antiderivative is half u squared log y parenthesis squared, and then plug in 5 and 1 dx. So we have that. Now this is equal to 1, 2, 3. When you plug in 5, that's a log of 5. When you plug 1, log 1 equal to 0. So that means you're going to have 1 over x times 1/2 log 5 parenthesis squared dx. Now you say half log 5 squared. That's a constant, we can move out. So 1/2 log 5 parenthesis square move out. Now 1 over x dx, the antiderivative is a log x. And then plug in 3, 1. So that's this part. And then again, log 1 equal to 0. So finally, we have this 1/2 log 5 squared. Notice this 2 you cannot move it down. Okay, if it's a log parenthesis of 5 squared, then the 2 can move down, but this you cannot. So we just leave it like that. Okay, so that's the example 1. Now, if you look at the example 2, okay, example 2, let's look at this one. We say sketch the solid whose volume is given by this double integral from 0 to 1, 2 minus x squared minus y squared dy dx. Okay, now here when we solve this, so first of all, let's look at the region, the planar region. So R is equal to, here is x, y, and then we say x is between 0 and 1, and y is between 0 and 1. Okay, first of all, we have this. And then we say the function z is equal to 2 minus x squared minus y squared. Okay, so now let's look at this. Okay, well, sometimes maybe you need to try to draw several graphs to see which angle is better to see. Okay, so I'm going to put in, this is the z-axis, okay, and then I'm going to put it like, say here, suppose this is the x-axis. This is the x-axis. Okay, and then I'm going to say, suppose this is a y-axis. Well, I expected that part, you're not going to see the whole thing, so I'm going to use a dash line. So this is a y-axis. Now you see, when x is equal to 0, y equal to 0, z should equal to 2. So that's this point. So this point is 0, 0, 2. Okay, that's on the surface. Now when y equal to 0, and then x equal to 1, so here is x equal to 1, somewhere here. Then you can see z must equal to 1. Z must equal to 1. So here we're going to have this piece. Okay? So this is a 1, 0, 0. Because we'll exchange from 0 to 1. Okay? And then let's see. Well, because I think I'm going to put it, this point is x equal to 0, y equal to 1. And then, let me see, here is a 1, okay, something here, probably that's here. Okay, yeah, it should be straight line. Now you see here, well, we're going to have when x equal to 0, z is equal to 2 minus y squared is a problem. Okay, so that's like this. When y equal to 0, and then z equal to x, yeah, I think I need to maybe change a little bit. Yeah, I think okay, you see, I probably need to change the angle a little bit larger, okay, because otherwise it's going to be blocking. Okay, so here, let me see. I'm going to do like this. Let me see. How about we just draw the regular one, the regular location position. Okay, how about we do like that, and then like that. Okay. So this origin, I'm going to put the origin here. So this is the x-axis, this is the y-axis. Okay, then, so here we have when x equal to 1, okay, then z equal to 1, y equal to 0. So this is 1, 0, 0. And then we have this point, okay, again, here is, let me see. So this point, of course, this point is 0, 1, 0. And then we're going to have, yeah, I think, yeah, let me see. Okay, well, in fact, we should be able to see this part. We should be able to see this part. And then here we're going to have a parabola like this. And then here we have a parabola like this. Yeah, I think yeah. Maybe I should draw the parabola a little bit better. Well, now let me see. Now we see which part we cannot see. Uh-oh, I think so here this part we cannot see. And then this part, yeah, I think and okay, now, well, if you think about when, for example, y equal to 1, which is a vertical plane, to cut the surface, you're going to have z equal to 2 minus x, the y equal to 1, you're going to have z equal to 1 minus x squared. That's a parabola. So in fact, it's like this, parabola like this. And also, when you let x equal to 1, and then you're going to have z equal to y, z equal to 1 minus y. Yeah, it's like this. So here, so this point, of course, is a 1, 1, 0. Okay. Yeah, I think maybe I should draw this one. Let me see. Maybe I should draw this the same height. Okay. Maybe a little bit higher. Okay. Yeah, I think a little bit higher. So like that. So then we say this top is z equal to 2 minus x squared minus y squared. And then this one, this part, the side is y equal to 1, and this side is x equal to 1. Okay, so that's like this. That's the solid. Well, use your imagination, and then you probably you can draw better picture than me. Okay, and then sometimes the practice get it better. Okay, let's look at another application problem. Okay, problem number 3. We say, oh, example 3. Sorry. Example 3. So we say find the volume of the solid in the first octant. Bounded by cylinder z equal to 16 minus x squared, and the plane y equal to 5. Okay, now this type of problem, you should be able to see the picture. Okay, so here, how about I'm going to draw the picture. Say here, suppose this is the z-axis. Okay, I'm going to draw some dash line. Okay, first, and then later on, if we don't need it, we are going to fill out. Okay. Okay, now you think about, say here, I think I'm going to, yeah, maybe I should put the z a little bit higher, but that's okay. I think I'm going to put it like this. So this is a z. Okay, you think about when x equal to 0, z equal to 16. So here, how about we say this is a 16? Okay, and then when x equal to 4, z equal to 0. Okay, 16, 4. Well, probably here. So this is a parabola on the xz plane. Okay, so something like that. Now, because z equal to 16 minus x squared is a parabola, and no variable y, that means y can be anything. But we said, suppose this point is a 4, 0, 0. This point is 0, 0, 16. Okay, and then this is 4, but we say y equal to 5. So here y equal to 5, that's here. So that means we're going to have something like this. Yeah, I think this is should be parent to y-axis. Okay, and then here we're going to have this. Now you see here is 5. Suppose here is a 5. Maybe it's a little bit longer. And then we're going to have something like this. Okay, so you see here, this surface, this is z equal to 16 minus x squared. Well, it's a cylinder, so the y can be anything, but we wanted we only want it in the first octant. And then this is a vertical plane. This is a vertical plane y equal to 5. Okay, of course, this is a perpendicular to y-axis. Okay, and then so here we said this point is 0, 5, 0. Okay, so that's like this. Okay, now you know the volume should equal to what? The volume is equal to x change from 0 to 4, y change from 0 to 5, and then 16 minus x squared, so dy dx. Okay, so it's like that. Okay, it's easy to integrate. So here we say this is 0 to 4. Well, 16 minus x squared is like a constant, 16 minus x squared. And then y is an antiderivative 1 and 5, 0. Okay, dx, well, that's just a 5. So now we're going to have a 5 move out. And then we're going to have a 16x minus 1/3 x to the third. And then plug in 4, 0. Okay, now you plug in 0, 0, plug in 4, so you're going to have a 5 times, well, 4 to the third is 64, and then here 64, so that means 64, and then 1 minus 1/3. That's 2/3. Okay. Okay. So this is equal to, yeah, I'll let you check. Say here, this is equal to, let me see, 2/3. 2/3 times 5, 10. The 2 times 5 is 10, so that's equal to 640 divided by 3. Or we say equal to 213 and 1/3. That's a volume unit. Okay, well, this section, I didn't talk about everything in the section. For example, the last part, the average value, that's just a formula. So I didn't talk about. Okay, please read this section. This section looks long, but we talk about a definition. Okay, because the definitions are important, we should understand where the double integral come from. And then we talk about a couple of examples. And the theorem, Fubini theorem, we didn't prove it. The book doesn't prove it. We use it. The proof is beyond the scope of this course, so we just use it to do calculations. The important thing is you need to be able to see the solid region. Okay, so well, of course, this is through practice. Do more problems, you feel more comfortable. So please read very carefully. Okay, I can only focus on the important part of this section, and then try to do the homework problems. Okay, okay. I'll talk to you next time. Bye bye.